Okay. This is what I'm going to describe as some research that my colleagues and I, Dick Morgenstern, Michelle Bell, and Jisheng Shi, did with under the sponsorship of Health Effects Institute. And the topic was to build a statistical model that tried to explain changes in concentration of PM2.5. I'll rephrase that here slightly to say what is the average concentration of, or average change, or average effect rather, of PM2.5 of emissions of SO2 and NOx on PM2.5 at various places in the eastern United States. And our study period was 1999 and 2005. In the terminology of environmental economics, what we're talking about here are transfer coefficients. You know, given a change in emissions at point A, what does that imply for changes in the ambient concentrations at point B? And HEI also calls this a form of accountability analysis, trying to see what are the effects of regulation. This is only a small part, but it's part of that. Brian also mentioned that there are new statistical methods coming along to deal with a lot of these problems. What I'm going to be talking about are old statistical methods. But in any event, let's get on. First, let me review a couple of problems that you might have in trying to get this. Well, we're thinking about a black box here, where emissions go in one end, and the black box works its magic, and then air quality comes out the other end. And so we're not trying to build in any of the physics or chemistry into that, except at an extremely rudimentary level. But what are some of the problems that you might encounter if you're trying to link utility emissions, and we focused on utility emissions in this, to PM2.5 concentrations? Well, one is that there's a relatively small change over a long period of time. I got here a little bit late, but I think Brian was talking about this right at the very beginning. He said that most of the studies like this have been done with big changes over short periods of time. Is that right? Yeah. Okay. And so this is a different matter, much more difficult to pick up these sorts of more subtle changes. The other point there, a second point, is that the effects connecting the source to receptor are likely to be highly variable spatially and temporally. That different sources have highly different effects on different receptors, and so you have to be you have to be careful about the way you model this. There are also many other sources of PM2.5 and its precursors. There are mobile sources, there are local sources, and what we're talking about is utility sources. You have to try to disentangle these in some way. And there are also these highly complex nonlinear weather and difficult in models like this. But we're trying to get an average, and so we're looking over a long period of time. Another point is that these receptor concentrations are likely to be spatially and temporally correlated, and in fact, this correlation declines with distance between the receptors. And finally, the plant level emissions can be temporally. They can also be correlated, and they can exert their effects from far away from the affected sources. One other point that or actually two other problems that didn't make it onto this list that I should mention is that as a practical matter, there's lots of missing data in the record. If you look at the receptor data, we focused on trying to look at monthly changes in emissions, the effects of monthly changes in emissions on monthly changes in ambient concentrations, looking how these monthly effects go. And there would be for most receptors actually there were quite a few months where there were no observations taken at all. Well, that came as a bit of a surprise to us, but it's the way it is. It was particularly bad in 1999, which is when our study started, because I think that's when the PM2.5 monitoring network was starting to ramp up, and so I guess it really is. We shouldn't have been so surprised not to find that much data, but we wanted to get 1995 in the study because there was that's when there was a pretty big change in PM 2.5 concentrations during that year. The other point is that another correlation I failed to mention was that the correlation in utility boilers between SO2 and NOx emissions is also very high. So we found that we couldn't use those in the same in the same model, and so we focused on SO2, but whenever you say that SO2 did this or SO2 did that, it's understood that we're talking about some combination of SO2, whatever those emissions are. And usually, at this time, there's usually, I think, about, I'm not sure, maybe 50% more SO2 than NOx being emitted. That's something in that range. The economy. Okay, there is a okay.
Yeah, it should appear if you just track that.
Okay, I'm doing that. Must be okay. I don't know.
Let's take a look here.
Am I so far off the screen?
It may be.
Oh, there you go. All right. You were right. Sorry. Okay. Okay. Yeah. Okay. These are ambient concentrations at monitor I, site T, and composed of four components. The first component is the effect of the emissions, and I'll get to those in a minute. And I've lost it again. Oh, there it is. And the second point is a temperature component. It's the deviation in the temperature in the month in question with the ambient temperature for all of those months. So it's January of 1999 relative to the average January. The third is a set of fixed effects, and right here, and these are interactions of each monitoring site and the year that we're talking about. And finally, we have a seasonal component, which are another set of dummy variables having to do with the month. So we investigated a set of models of this sort. Okay, now for the emission variables, the way we structured these is that imagine around each receptor there is a dartboard, concentric circles divided into wedges, and so we these are a figure, but here we have two concentric circles and 8 wedges, making a total of 16 emission zones. And what we do for each receptor, we add up all the utility emissions in the zone for that receptor. And so, for example, you look, we've got receptors 1 and 2 here, and a source at this point. Then the source is, there we go. Okay, is right here. Okay, and with respect to this receptor, it is this source contributes to the emissions in the sector outlined in blue. For this receptor, this over here are 2. It's the receptor outlined in yellow. Okay, and so with our initial hypothesis, or our working hypothesis, is that direction and distance are the primary contributors to the determinants of the effects that we're looking for. So this effect of the of this, let me find it. It's here somewhere. Here it is. That what we're assuming is that the emissions, the effect of emission sources here on receptor R1 are the same as the effects of emissions in this zone here on R2. It's a strong assumption, but we thought we would. That was kind of a simple thing to try. So that's what we were working. So that's basically what our model is. Okay, one last thing about the model is what the error specification is, and we assumed an error structure where there was a heteroscedasticity or non-constant variance at each one of the receptor sites, and within those sites, the variance of any particular monthly observation depends on the error variance for any particular observation depends on the sampling frequency, and these frequencies vary between 2 observations in a month and 31 observations in a month, and the ones with more observations got a bigger weighting. There's also a contemporaneous spatial correlation between the errors at the same time period, different sites, and those were a declining function of the distance between the sites. And finally, there's autocorrelation. Now, finally, getting on, I'll show you one result slide that we have after estimating this model, this regression model with this error specification, and we get results like this. And this is for a set of rings at 12.5, 25, 50, and so forth miles from the receptors, pretty much east of the 95th meridian in the United States. And what these lines essentially represent are, this is the effect of PM2.5 or the change in PM2.5 concentration with respect to a change in PM at each one of these distances. So, for example, if at this distance here, which is about a mean distance of about 20 miles, these effects show that on average, if you average this blue and red line, the contribution of PM 2.5 every 1,000 tons of SO2 and NOx increased PM 2.5 by about 0.15 parts per micrograms per cubic meter. And with respect to the results, there were I guess these things, these aren't totally. I think here there were some problems with the results obviously, but there's. Let me say a couple of things that I think that made us kind of that we were pleased with the results. First of all, almost all the coefficients were positive, and these were free coefficients. They could have been anything, and almost all of them actually were positive. Another effect is the effects generally decline with distance. So they start off with, and these are per unit of emissions. As you get further away from the receptor, the effects are smaller and smaller. And finally, you can see this blue line represents the strength of the coefficients that are on the west side of the receptor. The red line is those on the east side, and these western sources have a stronger effect on emissions than the eastern sources, which tends to correlate with the direction of prevailing winds. And so I think I'll quit there, and that's sort of the basic idea of what we did.